Welcome guys, in this new lecture we are going to talk about MCCB. Now, as we mentioned before, MCCB is used to protect your control panel as a whole. So you get your main cabling of 3-phase, you get it from the transformer or from outer source, and you connect it to your panel, but first it should go through one MCCB circuit breaker. This circuit breaker will serve two functionalities. One, it will cut the power going to your control panel. And second, it's going to provide a thermal protection so that if the cables got too heated up, you will protect your panel from any hazards. And two, a short circuit protection so that if the main power supply supplying your panel got shorted somehow, the circuit breaker will trip and protect your equipment. Now here we don't use an MCB because MCBs are rated at a maximum of around 100 amps. And usually if we have a large electrical panel, we might be having 300 to 150 amps or even more than that. So an MCB cannot handle such high currents. Another advantage is that MCCBs, you can adjust the characteristics you want for the tripping. So unlike the MCB who comes prefixed at a certain rating, the MCCB is adjustable at the rating you feel that will work best for you. Adjusting MCCB is not the same for all circuit breakers. Different manufacturer will have different ways to adjust the rating. But let's take Schneider here for example. Let's say we bought this circuit breaker MCCB and it's rated at 1000 amps. Now, we will give the rated current a symbol of IN. You will see this in any MCCB datasheet. It will give you IN is the rated current, and it will give you another symbol which is IR, which will represent a percentage of this rated current. And you will use this IR in order to define your tripping characteristics. If you look at any MCCB front side, you're going to see 2 or 3 screws that are rotatable. Now, one of the screws is going to be IR, which is again a percentage of the IN. You can take a percentage in between 70% and 100%. So if your MCCB is rated at 1000 amps, you can adjust the IR to 700, 800, 900, or 1000 amps. Now, the tripping curve will not be constant. Since the rating is changing according to our needs, the tripping curve will also change. So in order to know when will our circuit breaker trip, we need to plot the values that we have adjusted. Now let's plot a graph of current versus time, which is the tripping graph here. So IR can take any value from that horizontal space over here. Now there is another screw that will define the long time delay. The long time delay is going to be a line that will define how long will it take at a certain current for your circuit breaker to trip. However, to plot this line, we need 2 points. Like in geometry, to plot any line, you need 2 points. The manufacturer datasheet will define one of the points for you. Now, to plot a point, you need an X and a Y coordinate. So the datasheet usually gives you the X coordinate of the first point as 6 times IR. Why 6 times IR? If you reach 6 times your rated current, well, stuff starts to get tricky, and this 6 times IR shouldn't last much. Assume it's an inrush current, and inrush currents shouldn't last more than, let's say, 5, 6, 10 seconds. So this is the threshold for your circuit breaker, and it's starting to count. Okay, like 1 second, 2 seconds, I will be waiting for, let's say, 15 seconds, and I will trip because over that there is something wrong. So the first coordinate is 6 times IR, and the second coordinate will vary from one manufacturer to the other. In this example, it's taken at 15 seconds. So our first point is defined at 6 times IR and 15 seconds. Now there's two situations for this second point. Let's get to the first one. The manufacturer will define one of the coordinates as a fixed point. And in this circuit breaker case, they have defined one of the coordinates as 1.5 times IN. And in this circuit breaker case, they have defined one of the coordinates as 1.5 times IN. Why 1.5 times IN? Well, 1.5 IN is not really a tricky value. Remember, here we're looking at the electrical panel as a whole. We are not trying to protect a certain device. We are trying to protect the electrical panel as a whole. And from this point of view, it's fine to draw a current of 1.5 times IN, but not for a long time. I mean, this is the lowest threshold. Like, okay, at this current, it's fine to stay for like 4, 5, 6 minutes. But if we surpass this time threshold, well, then there is something wrong maybe, and maybe we should trip the circuit breaker. Now that the first coordinate of the second point is defined, we need the second coordinate. And that's the objective of the second screw, TR, or the long time delay. It will shift up and down along the 1.5 IN to define how long at this current value should it stay without tripping. Assume that we chose to stay for 400 seconds. So that means our second point is at 1.5 times IN and 400 seconds. So the trip curve in overall will look like this. Now we got a declining line. What does that mean here? Any current value in between 1.5 times IN and 6 times IR is going to take in between 15 seconds and 400 seconds to have the circuit breaker trip. At least 15 seconds and at most 400 seconds. Values that are less than 1.5 times IN are not going to be including in the tripping characteristics, so nothing is gonna happen, and it will be totally okay to draw a 1.4 times IN current without having the circuit breaker tripping. Now we've said that the trip curve is not constant if we change the IR value, if we change the TR value. So let's change the TR value and see what's gonna happen. And by choosing 120 seconds, this is what we will get. The purple line of the 120 seconds is declining more softly than the red one. And here it will take a maximum of 120 seconds to have the circuit breaker trip at 1.5 IN. Now let's get to our last point. Remember that I said there is two situations, that the manufacturer might define one of the coordinate of the second point. Well, sometimes manufacturer will not do that, and they will give you full control over IN within a certain range. And by that you'll have full control over the trip curve, and you can shape it the way you find most convenient for your application. Now let us Google one of the MCCB circuit breakers and see how we can extract this information we were using right here. Now for example, let's Google Schneider MCCB. And we'll click molded case circuit breakers. Well, this NSX series seems to get up until 630 amps, so let's choose this series. Well, let's choose a 160 amp circuit breaker. And the first result is 160 amps, 3 phases, 3 pole. Okay, we'll choose this one. Here they're writing 3P, means 3 poles. And then they're writing that it's AC, and it operates at 50 or 60 Hertz. And they're saying that IN, standing for rated current, is 160 amps. So here we got our first important value. Now our long time delay, they're saying that it is adjustable, and our peak time adjustment range is 0.7 to 1 times IN. So here's our second important information. Now here is the long time delay adjustment range. Here you will find your 2 points and their coordinates. So here's the first fixed point, which is at 15 seconds and 6 times IR, and the second point, which is at 1.5 times IN, and a second point of a range of 120 and 400 seconds. So this type of MCCB is the one without the IN adjustment. They give you first point fully, second point one coordinate, and you can adjust the second coordinate of the second point as you wish.